Ladies and gentlemen, welcome to our final session for our conference on joining and carbon engineering. I hope you enjoyed the lunch break, and we are looking forward to 3 further very interesting presentations. I believe we have titled the session that is following now Laser Innovations, and in fact we will, for the first presentation of this session, not look into laser welding, but laser-assisted inspection, so to speak. And I'm very pleased to welcome here on stage Professor Yeong-Do Park as our next speaker. Professor Park, welcome, and thank you very much for being with us. Professor Park is heading the Advanced Materials Engineering Department at Dong-Iri University, situated in Busan in Korea. And I'm also very pleased to say that we've heard you, Professor Park, numerous times on this conference before, and we're very glad to have you here again as a speaker, also in person, having traveled from Korea to us. Thank you very much for sharing your results again with us. We will hear your presentation on machine learning-assisted 3D laser vision for quality inspection of resistance spot welds, resistance element welds, and self-pierce riveting. We're very much looking forward to hearing your thoughts on this topic and your results. The floor is yours, Professor Park, please.
Thank you.
Thank you.
Okay. Thank you, Dr. Main, for the very warm welcome introduction. I'm Yeong-Do Park from Dong University in South Korea. Today's my talk addresses the machine learning assisted 3D laser vision for quality inspection of the resistance spot welds, resistant element weld, and self-piercing riveting. My talk actually focus on mainly on the quality inspection development, not the development of the 3D laser vision technology. So here are the agendas. First, the motivation of this development, and second, some challenges will be addressed, and also the development goal will be expressed, and I will provide some case studies for this development. Case 1 is the quality inspection of a resistance spot welding with a 3D laser scanning, and second one is quality inspection of a resistant element welding with a laser scanning, and then finally, case 3, quality inspection of self-pierce riveting with the 3D laser scanning. So modern car company adopts a lot of different types of welding and joining technology, such as the resistance spot welding or resistant element welding and self-pierce riveting to make the car body more in sound construction. And regarding for the resistance spot welding, it actually requires the free of the surface defects to guarantee the high quality. At the same time, the nugget diameter at the interface need to be large enough to guarantee the strong joints. In case of a resistant element welding, also same for the surface defects need to be controlled. At the same time, the weld diameter between the element and the bottom steel sheet need to be large enough to also guarantee the high strength joint. And lastly, the self-pierce riveting is the fastening mechanism, fastening technology you also know very well. It also, the surface defects need to be controlled, such as head flushness and bottom thickness, something like that. And also the internal quality will be the interlock, such as the very important quality for the strengthening mechanism. So all of these requires to guarantee the very good quality. There should be some inspection, quality inspection technology or method need to be introduced. And nowadays, widely used monitoring technology, there are the process monitoring, which is in situ, and also the quality inspection, which is ex situ. In case of the process monitoring, for resistance spot welding, a lot of dynamic resistance curve has been used to monitor the process and also power monitoring. At the same time, for self-pierce riveting, downforce or displacement can be also used. In case of quality inspection, the destructive testing has been also applied a lot, such as a peel test and tensile shear test. As you can see from here, this destructive testing is requires a lot of labor and cost and time, so which is not quite recommendable for the inspection. And second one is so to overcome these difficulties, non-destructive testing has been widely introduced and has been used. The first one is the visual inspection, which doesn't have the very high accuracy. And also the eddy current and ultrasonic testing, magnetic testing, radiography, acoustic emission, the thermography testing, all of those has been widely applied, and it shows the relatively very good sound inspection results, and people has been used for a long time. However, I was focusing on this visual inspection, and the reason is that why don't you have a visual inspection? What if you have a visual inspection with the high accuracy and also the fast and quantitative? If it can be done, I think we can do some very good quality inspection on the surface side as well as the internal quality. So for this reason, I will start to looking for some substitute technology to substitute the visual inspections. And I found some couple of technology. One of them is camera vision, which actually give us a lot of good information about the surface geometry. And also laser vision can be used, and laser 3D scanning. All of these technologies can provide can substitute the visual inspection and also provide a very precise and quantitative and automated measurement of the surface geometries. Regarding in case of this camera vision, it only can analyze the surface defects for the rigid spot welding. This is element welding and also self-pierce riveting. For the internal quality measurement, you need some more sophisticated and very delicate measurement of the surface geometry, which requires the level of laser vision and laser 3D scanning technologies. So from here, I'm going to address some of the challenges which I faced during the development. The challenges will be the quality inspection for multi-material joining, and also fusion welding and mechanical fastening need to be inspected. And also surface defects is very irregular and very hard to identify with the visual inspections. And also inspection speed need to be fast, and inline automatic quality inspection with the robot and internal joint quality inspection need to be done. At the same time, process monitoring has a limitation in accuracy, and surface defects inspection has also some limitation, and cost should be relatively low for the good application. So I decided to propose the non-destructive inline quality inspection system using 3D scanner, 3D laser scanner for the joint quality inspection here. A lot of OEMs around the world already start to use this 3D, either 3D scanning with a tracker system or laser vision system to detect any surface faults or any of the panel matching things. It has been widely used. A lot of new applications has been introduced, and by using these kind of technologies, we can actually scan the entire component surface and achieve the very detailed information about the surface geometry, including this one spot of the rigid spot welding in here. So by using this system, I start to make our goal for the development. The development goal was first, let's do the surface anomaly detection of the entire joint of the car body BIW, which is more than 1,500 joint. Secondly, inspect the internal joint quality with a non-destructive testing method. The internal joint quality can be the nugget diameter for rigid spot welding, and also the interlock for the self-pierce riveting. And third goal was implementation in series production with very limited time cycle, which was very challenging for our development. And quality check in body in white production with the machine learning technology, which is very interesting technology. So we decided to use this one for the development. Here are the case studies. First one is I'm going to share some of the information of our first case, quality inspection of rigid spot welding with 3D laser scanning. So it's a quality inspection, resistance spot welding quality inspection, which is with a non-destructive testing. It has some several requirements. One of the requirements is the automation and robust performance in the production cell, and also cycle time for the inspection requirement has to be less than 150 seconds for the inline production. And also inspection speed has to be one spot per 1 second. And secondly, very high accuracy on detecting the surface defects, and also the requirement was a visualization of each spot and statistical analysis of the joint quality in here. And classification of the surface defects of resistance spot welding, and also internal quality, which is nugget diameter estimation of resistance spot welding, also was required for this development. So to make this development, I'd like to record the definition of the welding. This is actually the mechanism of our approach. In here, definition of welding, as you all know very well, the welding is the fabrication process whereby two or more parts are fused together by means of heat, which is the thermal energy, and pressure, which provide the contact area, or both forming a joint of the part to cool. So which means that whenever there's a joint, fusion energy will make a certain type of a joint, which will have some contact with the pressure. You will end up with a certain type of surface geometry changes. In case of resistance spot welding, it will be the indentation on the surface of the here. So by thinking about this kind of the mechanism, we can actually most of the people already know that there is a high correlation between the nugget growth and also weld indentation growth, and also dynamic resistance curve. So resistance spot welding, when weld starts, the small nuggets start to grow at the interface, and because of this small molten metal developed in here, it actually yields the surface by the pressure applied from the electrode, and then the indentation will be formed along with the nugget diameter. And at the same time, the dynamic resistance actually value start to reach the maximum and start to going down because of this indentation formation. That's how the people start to use this dynamic resistance curve to inspect some of the welding quality for resistance spot welding. By the welding goes furthermore, the nuggets start to grow and more. At the same time, indentation size and geometry it become larger and larger more and more, and it will reach the end of the weld. So by looking at this mechanism and its well-known facts, we can say, well, then there will be very high correlation between the nugget growth and also indentation growth, and it should be the very linear relationship with the nugget and indentation of the resistance spot weld surface. Then, however, the problem is that this correlation is not simple and it's not quite linear. So there's a lot of the issues behind in here. The reason are these. But the modern recovery, we used a lot of different materials: mild steel, high strength steel, hot stem steel. Also, sheet thicknesses are very variety different, and also the sheet stack order are a lot of the combinations, and outer mild thin sheet, surface defects, upper sheet, and also bottom sheet, edge weld, internal defects, degraded electrode, and also variety of nugget diameter. With this complexity in here, the indentation of the weld on the surface, not a single indentation is the same. That's the issue. So, and then you can see from here, very variety of different types of indentation can be formed, and the challenge is how we can isolate these indentations and correlate with the nugget diameter in here. To overcome these challenges, and we have made two stages of the development approaches. The first one is machine learning assisted surface defect classification. Whenever we make a scanning of the entire component, we can actually isolate or extract the surface geometry of each weld spot, and we can have a point cloud data or STL data for the each spot welding. And then we can use this spot welding surface geometry to make a classification of the surface abnormality in here. We can actually use the convolutional neural network, and then for this development, we have used more than 7,000 weld of the surface geometry. We did all the labeling for each of them, and we did all the training for the convolutional neural network. And we did a machine learning, and it came out with quite good classification. It actually shows 6, but we can actually do more than 7 classification of the surface abnormal detections. The one is the normal weld, edge weld, tilting, surface exposure, electrode degradation, and pinholes. And we're still doing some more labeling and teaching and these days as well. And it shows above more than 95% of the accuracy for the prediction. And second stage is the nugget diameter estimation, which is a very challenging stage for us. And in here, we actually took this point cloud or STL data, and we made the cross-section of the scanning, and then we extracted more than 16 indentation features we took out from each single surface geometry, and then we used the artificial neural network technology, and also the algorithm has been developed for in here. With this development, we can actually, the output will be the estimated nugget diameter of each weld. At the same time, the quality result can be judged with good or no good. By using this developed technology, the validation has been made with the actual nugget diameter cross-section. Actually, this our developed algorithm we developed to predict the nugget diameter of the interface with the governing material thickness. So if you have a 3-layer stack in here, we always try to estimate the nugget diameter at the interface 1. And here is the first example, which is a small nugget with a 2-layer. Here's STL files of the surface indentation. It actually has a small nugget, 4.35 millimeter. Top side indentation, the estimation of the nugget was 4.41, and bottom side was 4.34, which is very close to the actual nugget diameter. In case of a 3-layer, even including the hot stamp steels, the very large nugget, 6.61, and estimated nugget diameter was 6.16 and also 6.34. In case, this is a very challenging part. In case of outer thin mild steels, actually the actual nugget diameter in this interface 1 was 2.81, which is provide very shallow indentation. However, even with this shallow indentation, we can actually estimate the nugget diameter. However, if you get to the more smaller nugget, the accuracy of the estimation become a little lower. So it's a little bit overestimated, but I think this is good enough to guarantee the good or bad weld judgment. And also degraded electrode tip we used, and then 5.06 millimeter has been measured and estimated was 4.45, and bottom side 5.10. The accuracy is in terms of the 10% range. And lastly, we artificially put some gaps and made a weld, and it comes with a very large indentation depths. However, the estimated value is very close to the actual nugget diameters. So with this kind of validation, what we can get is input data will be this point cloud data or STL from the scanning. And what we additionally need is because of the one complexity I introduced a few slides back, because of that, we need this kind of electrode information, tip information, also material information, the thickness information, or also the adhesive information. All those with the information, the output will be good or bad, no good judgment, and also nugget diameter estimation can be possible. At the same time, the surface abnormality can be expressed with the edge weld and those things. And these things can be done by our development system, which is actually the black box in here. Now I will introduce briefly how this process can be applied to make a very sound quality inspection in here. I will explain with the video in here. Oops. Okay. So we can actually, if you have any component, we can do this manual scanning. Also, it can be scanned by the pre-teach robot, and the scanning data will be for the component, and each spot of the scanning data can be extracted automatically. And then we did all this machine learning technology. We can classify this more than 7 different types of surface defects. At the same time, the surface profiling has been used for the feature indexes of the internal quality, and with the calculation and also the artificial neural network technology, we can actually do the weld quality inspection for each spot welds. We can report good or no good judgment. At the same time, the surface abnormality can be also reported at the same time. So here's our proposed quality inspection with the inline manufacturing for the resistance spot welding. We can actually, for the automobile production line, the welding quality inspection cell can be installed, and in this inspection cell, the 3D laser scanning or laser vision can be equipped in here and inspect any other surface qualities. At the same time, the weld surface scanning, at the same time, inspection can be done at the same time. So time required for the scanning and inspection is 1 second per spot, including the time required by the robot movement and laser scanning. It takes about 120 seconds to inspect 100 spots in one inspection cells. Here's the actual validation for the inline process in here. The laser scanning for the BIW, we can get this BIW scanning part, and also at the same time, automatic extraction of each weld STL file or a point cloud data can be done in here. After that, the one single surface profile or surface data can be thrown into this inspection system, and classification of the surface defects on the spot weld will be done. Also, report of the nugget diameter and quality inspection result will be automatically displayed in here, display systems. And this is, we can have this as a manual mode for the single spot analysis, and also we can do in inline mode. For the validation, we took any one component which has 202 welding spots, and we actually did the inspection, used the inspection system, and after result, we got a 4 spot which has no good welds. But in case of actual destructive testing result, it has the 5. So we have one missed the welding point. However, our system estimated a lot of warning, 17 spot of warning, but actual destructive testing only shows the 7. I believe that there should be some of the destructive testing, it has some inaccuracy during the destructive testing. A lot of weld has to be for the warning condition. But this is the interesting part, since we can have a surface abnormality detection in here, we did the statistical analysis for the 202 spot, and 50% of the very good weld, and 35% was a tilting condition by the electrode, and also 10% was welding was done by the electrode degradation. In here, our development entity system, all other ultrasonic and thermography shows the very good quality and speed. However, we can do internal quality measurement. At the same time, surface defects can be reported at the same time, and also the very fast scanning. We start to develop the aluminum resistance spot welding for this technology. It can actually, we apply the multi-ring dome electrode used, which shows the very variety of the ring traces in here, and also shows the traces of this multi-ring in here. But our developed system shows the very good correlation with the measured and predicted correlation. So we can probably be able to apply this technique in here. Our future technology is actually making the weld with the welding optimization condition program, which is already commercialized. We do the process monitoring. At the same time, we do the quality inspection with the surface geometry. If it shows the no good, then suggestion of the welding condition, this loop will continue, and it guarantees the very good welding things. Second is resistance element welding, which is, I will shortly make it short. This is very similar. It uses the same resistance spot welding machine. So for the bottom side, with the indentation, we can actually detect the quality inspection in here. At the same time, we'll use the dynamic resistance curve and surface abnormality detection. We use the same convolutional neural network technology to classify it into 9 surface defects for the resistance element welding. Finally, this is the self-pierce riveting inspection, which is I'm still in the investigation. As you can see that the self-pierce riveting is the technology which actually deform the bottom sheet into the die. And with this deformation will actually induce the rivet leg flaring, which means that if we don't have, or if we have some changes in deformation on the bottom sheet, deformation in here, this interlock, there will be some changes. So we can do field production in here. We can also vary the surface profile and monitoring signal by applying this surface profile, and we developed some of the machine learning technology, also some equation development. We were able to estimate some of the head flushness and also the interlock in here. These are the development we can for the surface defects. The die casting crack can be actually detected. It has been labeled and trained, so we can classify those cracks. And lastly, validation of estimation of the cross-section attributes. Here's the reference where the SPR, and with this measurement and predicted one-to-one correlation, if we have some abnormality in the process variables, it actually shows the very off data from the references, which with this mechanism, we can actually make some judgment of the good weld and, good SPR or no good SPR. In terms of interlock, also, the effective rivet length also can be predicted, and it was still this stage is under development. And this is the same technology. Also, all the training will be has been applied, just like resistance spot welding. With that 3D scanning, I think we can use this system to make inspection of resistance spot welding and element welding and self-pierce riveting with a very fast, precise, and quantitative measurement. I'd like to make some appreciation for all of my colleagues, my students, and also people from Test 1. They did most of the very hard work for the development. I only do the talk. Thank you for your attention.
Professor Falk, thank you very much for this excellent presentation. Impressive results, I think. And we'll take time, of course, as usual, to discuss the presentation. Are there questions from the audience? I see the first one here from Professor Böhm. Microphone is there already.
Yeah, thank you. Thank you for this great talk. You get all this information only by looking on the surface. Mm-hmm. Is it always necessary, especially for the resistance spot welding spots, to have a look on both sides, or are you able to get the same information only looking on one side? Because sometimes it's not possible to see both sides.
Right. Very good question. We actually faced those problems with, as I mentioned in here, in earlier, probably, the top side, bottom side, it has a bright difference of the panel combination. It actually had different geometry of the indentation. So we have to use some sort of the different algorithm for the top and bottom. Depends on which plate is on the top, which plate on the bottom. And with that, we kind of implemented some of the algorithm to make a same estimation of the...
Of course, I understand, but to get all this information about inside, structure inside, it's always necessary to have a look on both sides.
No. So only one side is required.
Okay, thank you.
Yep.
Do we have a question in the audience? Yeah. I would like to ask you one question about
okay.
I'm sorry. You're first, Sean, please.
Thank you. Sean Farrell from Gaming Engineering. Thank you, Professor Park. Very, very interesting. I'm wondering whether here you're looking at single spots. When you look at some of the errors let's say, worn electrodes could be repeated across multiple spots. Have you looked at, when you're correlating several spots in a row with the same gun, whether you can improve your prediction?
Yes, that was also a very good point. We actually experienced with the worn electrode, it actually gives the different indentation geometries. So we, for the same way, we implemented some of the logical the algorithm to compensate those changes with electrode degradation. And also, maybe the very challenging part was I don't know, I can move this one fast enough, but when we start to do the validation with the body in white, I found that there's so many strange, this is for weld, and indentation, which I never seen it before. So those are some of the challenges we have to overcome, and still we are working on that stage.
Okay. I think my question went in the same direction. Thank you.
Oh.
Do we have further questions to Professor Park? And let me also, in parallel, look at our online participants. No? If that is not the case, Professor Park, let us thank you very much once more for this excellent presentation. But of course, we would also like to present you with the tree we planted in your name, and it has become a tradition to make a photograph, I think. Please.
All right. Thank you very much.
There you go.